All right, guys, recording is in effect. I will then go over to the writing tablet on the other machine. So, so what is clustering? Clustering is a form of unsupervised learning. In other words, it is a form of pattern recognition. You're not predicting something. Prediction, if it happens, is a side effect. It's not the main purpose of clustering algorithms. What clustering algorithms look for are quite literally clusters in the data. Usually, you do have clusters in the data. They may be good quality clusters, or they may be not so well-defined clusters. But generally, data does not come as completely homogeneous. It's rarely like that. Most of the time, you do see patterns and clusters in the data. So the two kinds of patterns that we are covering in ML100 workshop are dimensionality reduction and clustering. So clustering was looking for clusters in the data. We covered k-means clustering. K-means clustering is the simplest clustering. It's a partitioning algorithm. Namely, each point belongs to some cluster. It does not support the notion of outliers. So every point belongs to this cluster or that cluster. Now, k-means answers half the clustering question. It says if you tell me how many clusters to find, I will find exactly those many clusters in the data. On the other hand, if you don't know how many clusters there are, well, tough luck. What you have to do is pick different values of k, try to cluster by that, and then look at a quantitative measure, something like a goodness of cluster measure, like within cluster sum square distance. Plot it out, you'll get a scree plot, and then look for an elbow in the scree plot. That could be it. When you find an elbow, you're lucky, you know that this is a good number of clusters. But if you don't find it, there may be multiple reasons. The most obvious reason that people assume is that there are no good clusters in the data. But actually, that's not true, as we did in the lab and found. You may have very good clusters, but those clusters may not be globular, they may not be roundish, right? Or convex clusters. When they are not like that, convex-like clusters, then you tend to see that k-means clustering does poorly. That was the lab that we did. So that's the limitation of k-means clustering. Otherwise, obviously, it doesn't deal with outliers very well. And not to mention the fact that k-means actually in high dimension can become computationally quite expensive. So with all of these things, there are many, many ways in which you accelerate k-means clustering, or you make sure that it doesn't get stuck in unstable clustering situations. What you do is basic optimizations, like if you have to do k is equal to 2 clustering, you'll take a random point and then you'll take the next point to be as far away from it as possible, and then do the clustering. And even then, if you suspect you might have been stuck with unstable solutions, you do the clustering again and again for the same k is equal to 2 and find which clustering gave you the lowest WSS metric and pick that clustering. So it's a little bit of an intense. The simplicity of the algorithm comes at a price because of its instability. You need to try it again and again and see which one gives you the best results. So in other words, there's something non-deterministic built into that. And that is that. But it's very easy to understand. People often ask, why is clustering not as simple thing as sorting and so forth? And the answer to that, of course, as we talked about, is clustering is not like sorting. We all have a unique definition of sorting, but with clustering, there are clusters within clusters, subclusters and so forth. So the granularity at which you're looking at clusters matters, which is what makes clustering a machine learning problem rather than a basic algorithmic problem in elementary algorithms that you learn in college. So that is clustering. With this is the scree plot that you build in order to come up with a cluster, the scree plot. Then it does, as I said, rather poorly when you have sort of a concave-like shape, or any shape that is not convex. When you do have, you may not get a elbow, or right. So that is something to be aware of. Another classic algorithm is the agglomerative clustering. Agglomerative clustering has the benefit that you can pick and choose how many clusters you want to see, because in one shot it finds from k is equal to 1 to k is equal to the number of data instances as many clusters. So you have all of those clusters are done and they are represented as a dendrogram. And so you have the benefit that once you visualize the dendrogram, you can pick and choose where your cutoff points are. You want to have a cutoff at 2, 3, 4. The model is built, and you don't have to rebuild the model for different values of k. You just have to slice the dendrogram at different values of k. In this, there is a linkage function. The question is the notion of distance between two clusters. How do you define the distance between two clusters? Is it the distance between two nearest points? Is it the distance between the center of the clusters? Is it the distance between the furthest points? Is it the averaged pairwise distance between by taking a point in one cluster and a point in another cluster and averaging it over? So there's so many definitions that you can use to define what is the distance between two clusters. Those are called the linkage functions because that's needed if you want to support the notion of distance. What is a distance? We talked about distance is actually, we always think of Euclidean distance as the bird flies or as we walk from house to house. But then there are many distances. If you remember, we talked about the Manhattan distance, and it's Euclidean is another one, and the generalization as Minkowski distance. But it turns out that distance is anything that has these following properties. Distance is a function of two vectors, let's say points x and y, such that the only way that a distance between the two can be zero is if the 2 points are co-located, sitting on top of each other. Also, distance is symmetric. In other words, distance from x to y is the same as from y to x. And distances are always positive. In other words, zero or more. The other thing is it follows the so-called Schwarz inequality, or the triangular inequality, which means that the shortest distance, the direct distance from x to y, will always be less than the distance between x to any other point and from that point to y. So this is a triangular inequality and often called it follows from the Cauchy-Schwarz conditions about distance or the notion of distance. In the literature, people often call geodesics, they use the word geodesic for the shortest distance. Now, geodesics are not necessarily straight distances. For example, on the surface of the Earth, when you go from here to India, you don't just burrow into the Earth and come out on the other side of the Earth. You instead follow the great arc. You follow the surface of the Earth, the airplane, and then it goes to the other side. For example, if you take the polar route, you go over the North Pole, and then you end up showing up on the other side. And it's a big arc. It's a great arc. So those paths are truly the shortest path, given the fact that you can't burrow through the Earth. And the word for them is geodesic. The generalized Minkowski distance we talked about, and then I also taught you about much more general things like the notion of metric tensors and so forth. When there's a deformation of the surface, complicated surfaces. We talked about density-based clustering. What does density-based clustering do? It is based on the intuition that clusters are regions of high density. If you consider each point to have mass, then clusters are regions of high density. And if you think that each point exerts a certain field or influence field, or creates an influence field, then you can find at any point in the feature space, you can find the net influence there. One intuition that I gave you for density-based clustering is think of these points as little bits of light, like stars or little lamps. And so at any point in the feature space, you're getting the light from all these data points or all these little lamps. Right? And so you get a total luminosity which varies from point to point. The way density-based clustering works, the state-of-the-art methods like this Denclu works, is that you ask this question: can I find my way to the brightest, most well-lit points? Those brightest points are called the attractors, and you do using a method that is almost identical to gradient descent. Here it is gradient ascent. You follow the direction of maximum increase. You don't go against it because you're trying to find the maximum. So that will give you that. The other method, which is a little bit doesn't scale, but also quite effective, is the dbScan. dbScan is well supported in Python libraries. Dentlo is a little hard to get. It uses the notion of neighborhoods, epsilon neighborhoods. So 2 points are directly reachable if they are within epsilon neighborhood of each other. A point is an integer point if it has sufficiently many neighbors within its epsilon neighborhood. So what you do is you take an integer point, you discover an integer point, and then you fan out from that and find all points directly or indirectly reachable from the integer point. And the set of all such points make a cluster. Then you go about hunting for another integer point not yet acquired, and then you start fanning out from that. And this way you can discover arbitrary many clusters. The beauty of density-based clustering methods is that you have a very natural separation between points that belong to a cluster and points that are outliers. And that's a significant benefit of density-based methods. So that is essentially a summary of what we have. And I wouldn't go more into the density based. And the DEN2, of course, we talked about. We have a net influence field, and given the influence field, all we have to do is the hill climbing method. This is this particular, the core of it is this. And I wish we could, let me see if I can color it somehow so that we remember it. Let me see. This is it. This crucial algorithm is the hill climbing algorithm. And the points we find are the attractors, the maxima. How do you know a point is the maxima? At that point, the gradient will disappear. And then, like if you think of single variable, univariate, then what happens at the maxima? If you go back and recall your calculus, at the point, at the top point, the derivative disappears, but then derivative disappears at the minima also, and it disappears at the saddle point also. So how do you know it's a maxima? The way you know it is that the second derivative is negative. So the derivative has to vanish and the second derivative has to be negative of a function. This is a recap from calculus. Its generalization to higher dimensions is the gradient has to vanish and the Hessian has to be negative. So that's sort of how you look at it. So that's about the trick. As a recap, any questions, guys, before I go to dimensionality reduction? Right, let me go to dimensionality reduction. Dimensionality reduction says that, let us say that the input feature space you are given. Is it at all possible that data is actually not uniformly spread and occupying the entire feature space, but it is actually occupying a subregion, a very limited subregion of the feature space, so that you can find a hidden surface or hypersurface, the technical word being a manifold, so that most of the data is sort of either clinging to it or close to it. It's very near that hypersurface or manifold, submanifold. So that creates the notion of dimensionality reduction. Implicit to dimensionality reduction usually is that whenever you do that, you implicitly assume that you can succeed at it. A priori, you don't know the ground truth. So should you try dimensionality reduction? How would you know when to try dimensionality reduction? The answer usually is you can never tell a priori, but you should always try dimensionality reduction. Because if you can reduce the dimensionality of the problem, you have reduced the complexity of the problem by a large extent. So there are many, many techniques for dimensionality reduction. The one technique that we've learned about in detail and is pretty much captures the spirit of other techniques. Others are more complicated versions, but sort of captures it as principal component analysis. So we looked at this data and we noticed that most of the data is hugging a line here. So that is our sort of the submanifold in this two-dimensional space. So how do we discover that? The way you do that is we bring in this concept of eigenvalue decomposition. So suppose we notice the fact that if you take uniform noise and hang on. If you take where is this? Yeah, if you take uniform noise and we we apply a covariance matrix to it, it will take on a shape. So we'll talk a little bit about the whole theory of it. Remember, principal component analysis works only when there's a strong correlation of data. Correlation implies a linear relationship. For example, if in the sine wave, the correlation is zero, the relationship is there, but the relationship is nonlinear. Principal component analysis does not work for nonlinear relationships. It only works for linear relationships. So it's a very simple model, a simple means of, not model, a means of dimensionality reduction. To understand it, we go back and recall what covariance matrices were. What is the covariance between two features? And I've just put it here. This is it. Oh, obviously, I noticed that I've messed here. I summation over I, 1 over n. All the averaging and all of that I had messed last time in the notation, I think, while explaining. But yeah, let me add that here. So what it does is, when you create a covariance between two things, means there is a relationship between one and the other. If one increases, the other increases, or contra increases, or contra varies, increases or decreases one way or the other. In one case, here, covariance positive means they increase together. Covariance negative means one increases, the other decreases. So now, with the covariance matrix, we took a detour into something, a little bit of linear algebra and the geometry of linear algebra. We said, suppose you have a point P and you rotate it with an angle theta. That rotation can actually be written, these are the basic trigonometric relationships of rotation. And this rotation follows from the expansion of cosine theta plus phi, sine theta plus phi. Actually, maybe I should mention what the phi was in this equation. This. So, and from that, we can actually work out that this matrix is the rotation matrix. Obviously, I'm going fast. If you guys want me to slow down and re-explain, let me know. But we have a lot of territory to cover today, so I'll keep it fast. Unless you stop. So this is the rotation matrix, basically. Besides rotation matrix, you can have scaling matrix. You can take a vector and scale it out, make it bigger or smaller. That you do with the scaling matrix. It turns out that the rotation matrix and scaling matrix are sort of the basic building blocks into which you can decompose any matrix. Any matrix will take a point and take it somewhere. Let's say P goes to P prime. You can think of it as a rotation and a scaling. And that's quite interesting that you can think of any transformation as a certain amount of rotation and a certain amount of scaling. And so you can see that the operation is, once you break it up into two parts, you can consider that any matrix is therefore made up of, any transformation is made up of something like this. Now, there's a very interesting fact. You take any matrix and you take all the points on a unit circle, what it will do is it will expand it out into an ellipse. You see this ellipse here. Now, you say that, well, why is that so? It will take you a little bit of time to realize that it will do that. But once you have convinced yourself geometrically that it will make a unit circle into an ellipse, you ask, okay, so what's so special about it? Our ellipse has 4 points that only scale up, they expand or shrink. But all other points, they rotate also. So those points are unique, those directions. If you take the unit vectors of these two directions, and of course they're opposite two other directions, but let's just take two directions, u1, u2. Those two unit vectors represent something interesting. They're called Eigen Vectors because this matrix only scales them up. In other words, if you have u1, the matrix M will just scale it by a factor lambda 1, and matrix u2 is scaled by a factor lambda 2. Lambda 1 and lambda 2 are called the eigenvalues of the matrix. The directions u1 and u2 are called the eigenvectors. And it's a very beautiful fact that this is true, that you can decompose it. And these are called matrix decompositions. There are other decompositions, singular value decompositions and whatnot, many Koleski decomposition, many other decompositions, with all of them with interesting interpretations. But eigenvalue and singular value are the sort of the crown jewels of linear algebra. A lot of the value that linear algebra brings to machine learning starts with these two decompositions, eigenvalue and singular value. But eigenvalue is something we learned about today. We will learn about singular value is generalization of eigenvalue to rectangular matrices. So one very rough intuition is that if you take a rectangular matrix and multiply it with itself, with its transpose, you'll end up with a square matrix. Once you have a square matrix, now you can do eigenvalue decomposition. So the eigenvalue of the square of the rectangular matrix is the same as doing singular value in the original matrix. That's sort of a very rough intuition. Now, what has all of that to do with our covariance? It turns out that you can create a matrix of covariance. Right? The principal diagonals are, of course, the variances themselves of each of the features, and the off diagonal is made up of covariance. Note that this matrix is positive, like it is symmetric. It is symmetric, and it has one quality. I think I should mention that for it is positive definite. If it is positive definite, what did I just do? Escape definite, which basically roughly translates that for any vector, this will be greater than 0. But let's not get too involved with those definitions. Basically, it means is that if it is a well-behaved matrix, then that matrix of covariance is something that captures the random noise and it will make it into your data. So your data's covariance matrix is what contains the information or the relationship of the data. If you can take any random noise and apply that covariance matrix to that random noise, and it will suddenly begin to look like your data, right? In linear situations. So therefore, this matrix is essentially, in many ways, you can say is the essence of your data. Now you say, well, that is all lovely. What can it do? The beauty comes when you realize that you can do an eigenvalue decomposition, and when you do it, you get lambda 1, lambda 2, the scaling across 2 dimensions. Now, one of the factors may be much bigger than the other. You can set the other factor to 0. Because you can set the other factor to 0, you have reduced the dimensionality of the problem. Right? You have essentially ignored some dimension which is irrelevant. For example, if you look at this picture, you can see U1 is quite relevant, but U2 can be ignored. It can be ignored because the scaling factor is a very small factor. And what we are saying is that if you just measure the coordinates or location of a particle, of a point along the U1 axis, it captures most of the information. You don't need to worry about U2. And so in such situations, you have reduced the dimensionality of the problem. So that is principal component analysis, guys. That is all there is to it. And so what you can do is you can represent the original uh, variables in terms of new axes, lesser dimensional axis. You have projected the data into lower dimensional space. One of the most common things to do is when you get data in high dimensions, just as a visualization technique, project it down to 2 dimensions. When you project it down to 2 dimensions, you can at least see the data. For the longest time, before more complicated methods came about, it was a pretty standard technique. Even today, your first line of action should be you take any data and you project it down to 2 dimensions using principal component analysis. Pick the first unit vector, the eigenvector, the second eigenvector, called the 2 principal components, and visualize your data. We'll do that in lab right now. When you visualize the data, you get some intuition of what you're looking at. And it means a lot. That will help you get some intuition in the data right away. Obviously, now there are more powerful techniques, for example, TSNE, locally linear embedding, and UMAP, and so forth. Today, I'll give you a taste of these things. We are going to cover these things in your ML200. ML200 gets, and then obviously at the end of this, I'll tell you what ML200 contains, but just giving you a taste of what is going to come. Are we together, guys? So this is a review of what we did the last time. Now, Principal component analysis, remember, is based on the fact that there's a linear relationship or a correlation between features. If the correlations are not there, it doesn't work. Now, just to remind you, remember for linear regression, if there is strong correlation between features, what happens? Is it a good thing or a bad thing?
Bad.
It's a bad thing. It leads to multicollinearity. The model becomes highly unstable. Right. On the other hand, principal component analysis is the technique which loves correlations because it sort of reduces dimensionality using that to a lower dimensional space. And so it is a common practice actually. It is useful that when you see strong correlations in data, first reduce the dimensionality of the problem so that all the correlations disappear. You're in a much lower dimensional space in which all the axes are truly independent of each other. The new features, the synthetic features, are truly independent of each other because then your classifier and your regressor will work very well. So the idea is you reduce dimensionality and then apply your classifier regressor, even clustering if you want. And I want to illustrate this with examples now. So with that review of that, let me move over to my Linux machine. I'm going to share. Let me see. Let me know, guys, if you're able to see my screen.
We can see it, though it's the kind of just the center.
Yeah, the text is only in the center, unfortunately. Let me do something different, perhaps. 1 second. Where's the sharing gone? I'll just share the browser. That might be more effective. Yes. Are you guys able to see it now better?
Yes.
Okay. Is the font size coming across big enough?
It's good size.
Yes.
It's a good size, huh? Okay.
It's missing the top.
It's missing the top.
We just see the component. Yeah, now it's here. Now we can see. Yeah.
Okay. So there is a particular data set that I'll use to describe it. Now, I was going to write this note, but I realized that there's a lovely article on towards data science that is worth reading. By the way, guys, I must also recommend. Obviously, I have no relationship with this particular website. I myself am one of the subscribers. But Medium, the website Medium, has a lot of very good articles. But in particular, towards data science, this particular thing, if you notice, they come up with every day you find new articles there. And well, you know, some people wake up and read the New York Times. Some people watch CNN. For me, my daily practice is usually when I wake up and have my cup of coffee, I come to this website. I visit only two things. General technology news I get from Slashdot. Some of you may know what Slashdot is. It's a techie kind of a website, a geeky website. And then the other is towards data science. Both of them will give you things that for people of our tribe is very relevant. I would highly encourage you to become familiar or just develop a practice to visiting uh, either this website or anything that is similar to this. But nowadays, there's a lot of other good websites also. But my first reaction is I come to this. I also check out, there are many competing websites which come out with news in this. The other, I mean, since this is the last lecture, maybe I can give you guys a sense of what all things I go to. One of them is Archive Sanity. I don't know if I ever told you guys about Archive Sanity Preserver. So a bit of a digression, but I thought I'll tell you. So how do I catch up? When I go towards data science, when I come here, where am I? Towards data science. I get the news, I get very digestible articles. Somebody has taken and explained something in great detail. You start by consuming a lot of these articles and then gradually feel inspired to contribute something back. I think there is a subscription. I don't know what it is, $2 or $3 a month.
$5 per month.
$5 a month, yeah. So if you guys can spare that, I think that's a pretty good utilization of the $5. Now, here's the best part. If you write articles for this website, I think you get your money back because when other people like your articles, you get paid for it. So it's it's sort of a community project, community site run by these guys, in which the more you contribute, you essentially don't pay anything. In fact, you get money back. A good place. The articles are really appealing, and so this is for learning. You know, these articles try to teach you some new topic. The quality of the article can be quite variable. Some of them are elementary, and you glance at it and you know it, or reading it is a waste of time. Sometimes the quality may not be very good, but broadly speaking, the quality is good. Right? And some articles are very good. Then if you go to Archive Sanity, it's slightly different. This is where I go every day to see what is the latest research. Actually, I don't go here every day. I take that back. I go here once a week, usually over the weekend. As a basic practice, every week I try to read 2 to 3 research articles end to end. Now, reading anything end to end takes a lot of time. So what will happen is I'll go here, I'll pick a 5, 6 of the articles. So what these people do is they take the best of the research that has been published recently. Right? So you can see the top recent, what are the classification-based anomaly detection for general data. Right? And it is just by the look of it, you can see that this must be a pretty good article. Let us go and follow it through. When you go here, there are only 3 citations, deep nearest neighbor detection, etc. But for something that was just published 5 days ago, the fact that there's already 3 citations for it is pretty good. Right? And it talks about, see, as you can see, let's read the summary of it. Anomaly detection, finding patterns that substantially deviate from those seen previously, is one of the fundamental problems of AI. Recently, classification-based methods were shown to achieve superior results on this task. In this work, we present a unified view and propose an open set method, GOAD, to relax current generalization assumptions. Furthermore, we extend the applicability of transformation-based methods to non-image data using random affine transformations. Our method is shown to obtain the state-of-the-art accuracy and is applicable to broad data types. The strong performance of this method is extensively validated on multiple datasets from different domains. So now if you're in fraud detection, anomaly detection, etc., this immediately, if nothing else, what would be your first reaction? Your first reaction would be, you would go, so there are 2 things I do. First is go look at the article, but even before I look at the article, what I usually do is I look at the references of this. So when I look at the references of this, and I find a reference, let's say this one, using autoencoders and nonlinear direction, let me go with this. This is a pretty recent. What can I do? I can look for citations. It has been cited in 38 other papers. So obviously, this is linked to some research, which is good. And geometric framework. So this is the way I would go about looking at things. This would be another article. I would go and see 247 citations. What does it mean? You just discovered a gem of an article. Somebody has done a lot of this is really a very good article, right? It has material, supplemental slides, and so forth. So now the whole question is, okay, you get a sense that this work is in the context of some very good work. What can I do now? What we can do is actually read the article. Just go here, and I'll give you a tip, guys, how to read this article. It's a bit of a digression. What you do is you just read the um, abstract, something that we just did. After that, you ask yourself, is it something relevant to me or not? Suppose you're not doing anomaly detection. You couldn't care less. You just move past this. You say, okay, done. Somebody has done good work. I'll remember that, but I'm not going to pursue this. But suppose you do want to, the first time around, don't read anything more than introduction. Read the introduction, right? And then just stop there and ask yourself at this moment, did you get the gist of what they're doing? Do you really want to continue? And then after introduction, go to the bottom. And in this, they are not only giving a survey, but they're also explaining a method of their own. So they have their own method, and they are claiming that their method is better. Decide whether you want to delve into their method or not. Is it of value to you? If it is not of value to you, it's good enough. You gained enough from the introduction, and you can move past. That is it. You stop at section 1, introduction. And now you can go ahead and read sort of other things. You can say, I'm done with this. I learned something from it, but that is it, right? And then this paper, by the way, is a very interesting paper, supervised contrasting learning. You come across a paper like this, and then your reaction is when you go and look at it, you feel, you look at this, you again look at the citations, at this moment only one citation, but you look at this and you feel, is it something that I would like to learn about? And once again, you go to the paper, you start reading this paper, and the first thing that strikes you is, if you're in this field, you will realize that, oh, like for example, my reaction was that, yes, this is directly relevant to me. I would like to pursue this paper more. Right? So once again, you do the same thing. You read the first section, maybe the second section in this case. You determine whether you want to pursue this or not. Right? And should you decide that you do want to pursue this, you ask yourself, can I just glance at the equation and tell what is happening? So, for example, can I look at this and ask, how is it different from the loss functions that I'm used to? Well, this gets a little bit mathsy when you do engineering math with me, math or data science with me. You learn to recognize it immediately, that how is this different from what we have been doing? And that is a crucial thing to first right away identify, why should I read this paper? What makes it so special? What is the main contribution of this paper? Once you do that, then with sufficient mathematical background, you can easily start breaking it up into pieces, like positive cases, negative cases. Pretty much the same thing you do for a classifier's loss function. Then this is talking about, this may remind you a little bit about, for example, softmax, so somewhat like that. But then you start looking at it and you ask, what is the advantage? How much better does it do? Clearly, if you're using the simple loss function that we did for classifiers, if you remember that, the maximum likelihood estimation based loss function for classifiers. So it is saying that if you use that for all of these architectures, these are neural architectures, you get this level of accuracy. But if you use this method, supervised contrastive, the gains are astounding. You realize that ResNet 50 all of a sudden gives you from 70, well, okay, it gives you a little bit better, and top 5 has really climbed up to 93 and 95%, which is good in the sense that if you look at ResNet, well, not always good, but okay, so a little bit good here. You look at this. In general, what do you get? Do you think that it's an earth-shaking improvement? May or may not be, but it is certainly an improvement. It's certainly worth learning about. And so you learn about it, you go read it. In fact, I found it to be interesting. So this is, anyway, this was a bit of a digression, but I thought I'll introduce you to how I stay abreast of the field. How do I stay um, with it? Like, keep in touch with it. Am I able to keep in touch with it? No. Almost every day, somebody points out things to me that are very crucial developments that I entirely miss. Sometimes I miss them by 2, 3 years, and they happened while I was busy doing other things. So we are always in a catch-up game in this field, but we all have to have a framework to stay in touch. So, well, anyway, so much for that. So I'll come back towards data science. Let me give you a little bit of a background on the breast cancer data. Those of you who did the boot camp with me, of course, are familiar with this breast cancer data. We'll do the breast cancer data in great length in ML200. The history of this data is this. As you know, breast cancer is not at all a visitor that you want in your house, ever. It's a pretty nasty disease, and women are quite scared of it, very, very scared of it. So it can strike anybody just about. And so people get tested, they get mammograms and so forth, taken, I believe, annually or something like that. Now, suppose the physician finds, the diagnostician finds some hint or suspicion that there may be lump or something like that. Then you get more invasive. The second line comes in, which is that now, lumps can be pretty harmless, but it can be serious. If there's any anomaly detected in the X-ray or in the mammogram, then the next line of defense is you would go and do a core biopsy. You would go in to that lump, take tissue out, look under the microscope, and so forth. Well, that remains a gold standard, but sometimes people ask, that leaves a scar. Can you do a little bit non-invasive version of that? So in the late 1980s, early 90s, the thinking was that, can we do something called fine needle aspiration? We go with a long needle, thin needle, to the lung, just aspirate out a little bit of the tissue, look under the microscope and tell whether there is cancer or not, or it is a benign cancer, benign tumor or a malignant tumor. Then when you do that, the trouble was that the human accuracy was quite imperfect with fine needle aspiration, which is why even today diagnosticians in US, for example, with suspicion you go directly with core biopsy. But in a lot of countries where core biopsy is expensive, people usually in India, for example, the first line of action, if there's a suspicion of tumor, is to go with fine needle aspiration. Non-invasive, fairly economical. You aspirate out a little bit of a tissue, look under the microscope. If you see, you still suspect something is wrong, then you send for further testing. But the trouble was that even people who were experts at it, their accuracy wasn't very good. One of the questions that was raised is, and it was very time consuming and labor intensive. So the question raised was, can we do an automated machine learning based detection or classification between benign and malignant tumor by looking at the image of the fine needle aspirated tissue? And so a bunch of researchers, they spent a lot of effort onto it. What they did is actually one of the great, really beautiful exercise in feature extraction. They look at the diameter of the cell. They look at the cells, if the tissue cells, if they look concave, if the surface looked regular or irregular, what was the size of the cell in the tissue, and so many, many markers. They looked at some 23 markers, and based on those markers, they tried to build a machine learning model. When they built a machine learning model, it was quite a success actually. It gave 90 plus percentage accuracy, right? And the recall was pretty good. So people began to use it. I mean, fine needle aspiration now, especially in a lot of countries outside US, is pretty well established for as a quick diagnostic measure. But using machine learning, of course, you get much higher accuracy. The use of machine learning itself, it turned out that was not very prevalent because then the equipment becomes very expensive that can do it. Certainly, it's a good machine learning exercise that we are going to do. So, machine learning is still permeating the world of medicine slowly. And then, as I said, the next 10 years will go into applying AI to the medical domain. Almost all of you, as you become machine learning experts, my feeling is that in the next 10 years, you will sooner or later work for a company that is doing uh, medical AI. One way or the other, you'll end up doing that. That's the new frontier, just as the 2010 to 2020 when to such a large extent to image processing. Self-driven cars was an ambition, a lot of classification and text recognition, image recognition and image segmentation. And those will continue, but I feel that medical AI will become a big topic. So we have this data set. I would highly recommend you to follow each of the steps in Python. You take the data, you look at it. When you look at the data set, you will realize that there are 357 cases out of this many where you do have cancer. People do have cancer. If you visualize the data, this is just making the pair plots, guys. By the way, I wouldn't recommend the code that he has used. I would recommend the code that I gave you in the tabular data notes, because that code will immediately draw essentially the same histograms and pair plots for you in a perhaps more elegant manner. So you use that, and then you realize that when you look at the data, the features are highly correlated. Let's look at this feature: worse symmetry and worse texture. So find tissues with the worst texture and the worst symmetry. What do you notice? Is there a correlation between these two features, guys? Is there a linear? Are they positively correlated? They seem to be, right? The bigger the symmetry, the bigger the texture, the worse texture. Likewise, mean radius and mean concave points also are correlated. You can see a the positive correlation between these two things. So you see these. When you see correlations, you realize that PCA would be quite good actually in these situations, because it will remove all the correlations and take you to a lower dimension space. By the way, yeah, this has about 30 features. I said 23, 25, now it's 30 features. So you take these features. Now what you need to do with PCA, and something you need to be sort of careful or aware of, is PCA works with correlation. Correlation, remember, standardizes the value, x minus mu over sigma, if you remember the theory we did. So in Python, it's a one-liner. You just take a scalar and you can scale the data. It will scale it to a standard scale. And then the PCA part is unbelievably simple. Like I told you, clustering and PCA, unsupervised learning, from a coding perspective is extraordinarily simple. 2 lines and it does it. And when you do that, you look at something called, if I go to lower dimensions, so suppose I say I'm going to just pick 2 dimensions, then what proportion of the actual information that is there in the original data set can I explain with this reduced dimension of 2? It's called proportion of variance explained, POV. So it's a technical term, and the book is clearly explained, but that's about it is. Think of it as how much of the information did you capture? And so to capture that, you look at it and you realize that the numbers are like this: 60, 26, 12. Right? So the first dimension captures 60% of the information. Second captures 26. So what is the addition of these two? 60 plus 26 is 86. 86 plus 12 is, or 13, is 99, isn't it? And so what it means is that the first 2 dimension captures close to 87, 86%, and the third dimension added captures most of the information, 97% or so, which means that in this case, dimensionality reduction would work very, very well. And you can see that just in 2 dimensions. Do you see that the data point, when you project it down to 2 dimensions, first principal component, second principal component, what do you see, guys, here in this picture? If you look at it, do you notice that the benign, the green cases and the red cases are well separated out? Do you see that, guys? It's remarkably well separated out. Guys, can you hear me?
Yes, it's very well separated. Looks lovely.
It's lovely, yeah. And it's really good. And if you do it in 3 dimensions, it gets even better. So with this data, guys, if you were to use any classifier, let's say logistic classifier or linear discriminant analysis or whatever, you realize that you will have a near success. Immediately, you'll have a very high degree of success, isn't it? And that is the beauty of PCA. You get a model. very interpretable, and you get a simple interpretable model, and you get a good classifier. That is the beauty analysis.
As if what three components did he pick?
No, the machine. Those are
Oh, the
specific
machine.
components.
The machine just. So the machine just
Oh,
the
Gaussian
actual
and
algorithm.
Right?
So the actual algorithm was the one that looked for the correlated components.
Yeah. What the
And then
algorithm
computed for lambda.
What the algorithm did is that it found these hidden dimensions. Remember, these are not the original features. It is not the first principal component and the second principal component are any one of those 30 features, but it is a mishmash of those features. Remember, it is a synthetic feature created by bits of the original features, little bits of the original features. And because it created the first and second,
So as if okay.
go ahead.
So it's like when you say it got components of one feature and the other feature, it's like getting the BMI of a patient based off of height and weight, something like that. It figures
Yeah,
out
sort of like
the value of BMI, something like that.
yeah, the intuition is
Body mass index.
intuition is that a BMI we take as a number, but it captures two things. It captures the height, weight, and so on and so forth. So it's just like that. BMI is a good example. So these principal components are like BMI kind of thinking. They are a mishmash of other features, all the original features. When you do that, now typically what happens is when people do it, uh, especially in the medical domains and in the biological and a lot of it in the economic domains, people get used to these components and they say, what is the intuition behind it? And sooner or later they give an interpretation. They give a physical intuition, like BMI has become an intuition that is very, like, you look at a person and you can sort of guess the BMI these days, right? So it becomes something, a word of its own in the literature, and people start developing intuition about it. So that is what this thing is about. And look at how remarkably successful it is for that. And you can do that. Like if you can ask yourself that originally there was so much correlation in the data. Now, once you take the three principal components and what is the correlations now? You realize that very little correlations. They're all close to zero, minus 0.3 to 0.3, which is small correlations, and all the correlations stay strong. Whereas in the original data, the correlations were very, very strong. You see that correlations of 1 and so on and so forth. So that is it. Now you can say, well, this is half the problem. Where is the classification part? Can we see the classification part also? So that is a separate post actually the same author has written. Let me go to that. Yeah, and it's beautiful visual. Sorry, I apologize. I think we are jumping around somewhere. Yeah, beautiful visualizations. Yeah, it's you notice this pattern in the towards data science articles. Sometimes they'll all try to start with some grand picture, a banner picture, and which will be tangentially related. Here is a bridge, and he's calling it a decision boundary. Well, I'm not so sure it's a decision boundary, but for what it is worth, it's there. But just to make the page more colorful, I suppose. So this one is the same thing. You take the code, you do the principal component analysis, repeats it here. Once you do the principal component analysis, you look at a pairwise many features. Okay, after you do the PCA, you realize that you can cut the data pretty well using this. It's the same thing. Data is very well separated. What can you do then? You can then, well, there's a little bit more. You can apply a classifier called support vector machines. I would say, and this just illustrates the point. Support vector machines is something you'll do with ML200. By the way, you could have just used logistic regression. It works just almost as well, and it is something you are familiar with. So when you do that, it will come up with a classification accuracy, which is very good, 94% accuracy. 94% is not something to be not impressed with. It's pretty impressive. You got a very good impressive. And if you look in terms of plotting the support vector's decision boundary, you see how clearly it is. But do you see that, guys? That you can directly draw a line between the red points, the malignant, the malignant and the benign points here. Here the green is malignant and the red is benign. Do you see this, guys? It's a very simple idea. There's nothing very complicated to it. And if you look at the entire code, it's very short. Here, you scale the data, you pass it to SVM, to PCA to reduce the dimensionality, and then you just give it to a SVM kernel, and then you use it to classify. The rest of the code, all this is just visualization code to create pretty visualizations. And it creates a nice 3D animation. You can see that if you use 3 principal components, then data has even better separation between the. I don't know if this visualization conveys it, but if you look at it carefully, you'll realize that just 3 dimensions were enough to separate the data out. Now, this is not a toy example. This is a real data set that was one of the landmarks in machine learning history. And we won't go into SVM here. Just imagine you're using logistic regression and this thing would work. So guys, what I'll do is I'll post these 2 articles into your Slack. And if you like, usually you're allowed a certain number of articles free per person if you don't have membership to this. If you can't access it, let me know. I think it may be okay for me to post a PDF of it. I'm not sure. Let me post these 2 right.
Oh, Asif, actually, you have 10 full views a month for towards data science. But after that, when you go on your 11th article, it gives you a preview. But if you copy the URL of that and paste it in an incognito browser, it gives you the whole article.
Article anyway. Okay.
Yeah. So you can just view the links in incognito, and yeah, you don't have to pay.
My daughter told me that too.
Right. Though, as a person who spends a lot of time writing articles and notes, I would say that pay that $5 to this very poor authors. They put in a lot of effort in doing that. See, guys, we are engineers, but we are paid what, $300-400 an hour, and it typically takes to write an article easily 8-10 hours of effort or 12 hours of effort. It's thousands and thousands of dollars of value, economic value, and you just give it to these websites. When people read it, if they all just contribute, like per article, there'll be like 10 cents. 1,000 people read it, it's still just $100. So writing books, textbooks, and technical articles, remember, it's not really for the monetization aspect of it. You do it for because you love the subject, you want to show it, explain it, do things like that, I hope. And sometimes people do it for name and fame. So, but in any case, it's a good way to say thank you. After all, it's just $5 or whatever, $2 in some websites or $1, something like that. So, all right, guys. So what I'll do is these are 2 articles. I put it on your towards data science. Do try to work through the lab. The first one, which is just the PCA, do the lab. It will just take you half an hour to do the lab in that. And the second one is for you to know for the future. So what I'm going to do is take a maybe, should I take a 5 minutes break? Or what I would like to do now is give you a preview of what is coming in ML200. Would you guys like that? Or have I given you an idea of what's coming in ML200 already?
You can tell us again.
Or maybe, yeah, I could tell you guys again. Let me go and see. It might be in the website itself. Oh goodness, I need to move my website from Norway to US. It's too slow there. Let's look at workshops. Okay, intermediate data science. Okay. Capstone. Yeah. So these are the topics we'll do. We'll do the no free lunch theorems. It's something very important, but most textbooks miss it. Then we'll do support vector machines, as you can see. Why is this like this? Minus. Okay. I don't know why it is behaving like this. Let me put it in the incognito mode. Are you guys seeing my screen? What are you seeing? Anything at all?
I'm seeing
Let me.
Capstone ML200, no free lunch theorem, support vectors machines.
Okay, you are seeing
Website.
that. Okay.
Yeah.
So, yeah. Okay. So in this, we'll do gradient boosting methods, random forest and extremely randomized trees, decision trees, ensemble methods, bagging, boosting, stacking, kernel K nearest neighbors. We'll do the art of feature engineering. So these were the 9 topics that are there. 9 or more than that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 topics. But actually, I added a few more. The a couple of more topics that we will add are bit of see regularization is not here. We'll do regularization. It's an important topic. And the other thing is recommender systems is not here. We'll do recommender systems also. So there'll be 11 topics and they're about 10 sessions. So we'll move a little bit fast. We'll cover a lot of territory per session. Obviously, for each session, I'll try to give an extra session also so that that compensates for that. Any questions, guys?
Not for me.
So these are the.
We have a sentiment
What's that?
analysis. Sentiment analysis.
Very, very simple, easily. Why don't? All right, we'll add it. If you guys want sentiment analysis, surely we can add it. So it's a pretty large scope. You'll realize that the intermediate machine learning moves much faster than the normal, than the ML100. One thing I would suggest is do all the labs of ML100 so that you're mentally prepared for ML200. And those of you who are taking it, please, and this is a plea to you guys, do please pay and register. At this moment, support vectors need some funding. Desperately, the pandemic hasn't been very kind to us. So, with that, that's all I have actually, guys. So, with that in place, I would say that I'll just field questions now. I don't have anything else. Principal component analysis was a simple topic, but guys, if you don't practice this, it's of no use. So make sure that you do practice it.
Okay.
That is sort of important that you practice it. And it will take you barely half an hour to do. See, dimensionality reduction is one of those most awesome things. It is mostly understanding it. Once you have understood it, the coding is almost trivial. Nothing to it. Very quickly you are able to do it. And the bang for the buck is enormous. Imagine just 4 lines of code, and sometimes you have great success with it. Are we together? So these are the topics we'll cover. Now, one thing I would do is I want to give you an idea, perhaps, of other dimensionality reduction techniques. PCA is the basic. In the next workshop, we'll cover some more dimensionality reduction techniques also. Let me give you guys a sense of that. 1 second. Let me share the screen. Maybe I could use that to share that. Where now? Oh, okay. In progress. Here we go. Application window destination. So are you guys seeing my PDF?
Dimensionality Reduction toolbox in Python.
Oh yes, thank you. Thank you for verifying that. So this is an article again taken from towards machine learning. Somebody has put together. This is something you'll see. People have contributed a lot of effort in explaining to each other different topics. And the idea is that if we all explain to each other, we all benefit. So again, as a best practice, as a parting advice, I would say, pick up a side that you like. Towards data science is pretty good. You can pick up other. And every day, sit down with a cup of coffee and pick a couple of articles and read through the whole of it. Most of these are very quick reads. It says 5 minutes. Well, 5 minutes is a little bit of an exaggeration. I would say you can actually study it in about 10-15 minutes. Right? 5 minutes, you can glance through it. But if you understand what it is, you'll start with, you look at these imports. You don't have to study the imports line by line. Then you take the MNIST data set, which is a digit recognition data set, handwritten digits. So it's a standard data set that for years has been a classic. Can you recognize a handwritten 9 or a handwritten 6 or a 8? So for many, many years, it has been sort of a benchmark. So this does, and it says the dimensionality of the data is 784 dimensions. What can you do? Obviously, it's too many dimensions. Can you reduce the dimensionality of it? So to do that, once again, guys, do you notice it's just 3 lines of code? In 3 lines, we are able to reduce the dimensionality. After that, there's a plotting code, which is a bit tedious, longer, but very simple. All you're doing is attaching a color to each of the digits, 1, 2, 3, 4, 5, 6, 7, and you're plotting it. When you plot it, clearly you notice that, for example, the zeros are clustered here, the blues, ones are clustered here. So 0 looks very different from a blue in a synthetic Pca space. Right? And different digits get separated out. It's pretty impressive, right, what Pca can do. Now there are enhancements to Pca. Right? People have created quite a few enhancements. So there's something called incremental Pca. So you can work with batches of data. So just keep this image in mind, and now look at doing it using incrementally. This may or may not be a little bit better than the previous one. But this article showcases all the ways that you can do it. Then you have something called the Kernel Pca, very, very powerful method. Actually, we applied it in the bootcamp to the breast cancer data set with some interesting results. But for what it is here. This generally outperforms Pca by a little bit. At this moment, we don't have the full experience to notice it. That is one. The second thing is that in this particular example, it doesn't seem to outperform by much, but for what it is worth, it is there. But do you realize that this is just 3-4 lines of code, yet another dimensionality reduction method. Another is called Sparse Pca, which uses, there's a little bit of mathematics you learn in the math of data science, but from the coding perspective is that, see, here's the thing, guys. If you just understand Pca, you can use fancier methods even before you understand the mathematics behind those methods, because it is just changing one word. Do you notice between kernel Pca and this? All you do is change the word kernel to sparse, and now you're on the go. Right? Singular value decomposition, right, leads to a different kind of result. Singular value decomposition is like eigenvalue decomposition I just talked about. The results are like this. Then you have something called Gaussian random projection. One more interesting method, which produces, well, probably not so impressive in this particular case. All these different types are literally sitting on top of each other, not very impressive. Then there is sparse random projection. You look at sparse random projection, again, not terribly useful. Then comes some more powerful methods called multidimensional scaling. Look at this. Well, unfortunately, this picture is reduced in 2 parts in this PDF. But if you can clearly see, the separations are slightly better, much better in this. You can do ISO maps, which are also reasonably good. Mini batch dictionary learning, not at all impressive for this particular situation. There's something called independent component analysis. A bit of a disaster here, but okay. But then comes a very, very interesting method. It is called TSNE, T-Distributed Stochastic Neighborhood Embedding. Quite a mouthful. Very powerful methods. And if you can look around it, you can clearly see that as a dimensionality reduction technique, this has worked clearest. Isn't it, guys? Do you see that the clusters are fairly well separated? It's not perfect, but it's pretty well separated, isn't it?
Definitely.
And that is that. Then there's locally linear embedding. It produces this, not too good. Now the question is, which one should you use? The answer is a priori, you can never tell. It's part of something you'll learn in the next class, the no free lunch theorem. So what do? I actually have an automated loop that generates a two-dimensional representation using each of these methods. We live in the world of computational plenty. In cloud, you can have as much computing resources as you want. You can spin it up for just 20 minutes and then shut it down. And you'll, even if you use yourself a very, very a powerful instance, you would probably consume what, 10 cents, 20 cents of it, and then you shut it down. But you get all the results and you'll know which is the best. Autoencoders again has to do with deep neural networks. Is it good? Yeah, it seems to be getting there. Some of it got very well. Others it didn't do such a good job of. So this is it, Now there is one more new kid on the block. It is called UMAP, which actually usually outperforms TSNE. This article doesn't mention it, but I would give you the idea that, guys, try out this. And then try out these things, especially because they are all just one or two lines. And it's very gratifying to see how well the data separates out like this. So go back to the breast cancer data itself, if you so wish, and try to apply all of these techniques to it and see what happens. So, well, guys, that's it. That's it for the extra session. And I don't have anything else except to exhort that you guys do these labs. Very simple labs. Do you realize 2 lines, 3 lines of code or algorithm?
Sorry, Asif. So
Yes.
if we're good in performing PCA, does this save us a trip from consulting with the SME? Or do you have to consult first with the SME before going to the PCA? Because of confounding variables.
What happens is that you should spend a lot of time analyzing before you talk to the SME, because you're entering somebody else's data. The experience shows this. It used to be believed that without SMEs, without subject matter experts, you really can't analyze the data. They know it. Then came an inflection point in data science and machine learning. It turned out that machine learning was making much better predictions than SMEs. And it was a surprise for everyone. It turned out that the theory or the beliefs in the different subjects sometimes were a block. They were preventing those people from seeing things which was not there in their belief systems and their theories. So machine learning started outperforming the SMEs. Today, the situation is if you combine SMEs and machine learning, you get the best of both the worlds. A classic example is, how do you build sports teams? At one time, people would build sports teams using as subject matter experts. Scouts with a lot of experience would know and observe players, how well they play, this and that. Then came machine learning, and it applied just statistical analysis and said these players should work together and they will win. You form teams using machine learning, and that what is it, curveball or something? It completely hardball. I don't know what apparently there's a book or a show by that name. I'm not at all into sports, but apparently it used to be a big thing when this was discovered. And so today, machine learning beat the accuracies of those veteran scouts. Today, but then somebody should, of course, that if you combine the veteran scouts and machine learning, then you have superlative, like you have the best of both the worlds. So that's how it is. Do a lot of analysis, then sit with subject matter expert, listen to what they are saying, and then go and do more analysis. That is usually the cycle. See, machine learning is not a linear journey. It is a cyclic thing. You keep cycling back to, you're chasing your own tail for a long time. You keep going back and again and again. So the way I would say it is, it's like a rising spiral. You know, at each cycle, you rise up a certain distance, your accuracy improves. And then you cycle back and you cycle back and you keep cycling back. But at each time, you're not coming back to the original place. You're rising up along the z axis. You're learning a lot and your models are getting better and better, even though you seem to be cycling through a lot of the ideas over and over again, going to subject matter experts, cleaning the data further, doing more feature extraction, then more model building, then once again making predictions, then going back to the experts, then going back to data, doing more feature extraction, more cleanup. And that cycle typically goes up. See, remember, with one model, I'll give you an example. In my team, I lead a machine learning team. There are people who for 7 years have worked on only one data set and one problem. Like imagine a group of 6 people who have done nothing but try to extract value from one data set for 7 years. So in reality, what happens is when you join the workplace, you will get 2-3 data sets which will become your life. And for a couple of years, you will be spending all your days trying to do the best you can with those data sets. In the homework, it seems, right, that quickly you finish one data set, you move to the next and the next and the next. In work, it's not like that. It takes a long time to squeeze the juice out of a data set. Take, for example, the situation with Zillow. Zillow makes house predictions. It's a regression problem, isn't it? Very much like California data set predicting the value of a house. But they weren't quite accurate. They were much better than what was before. People trusted Zillow and Trulia, all of this Trulia and so forth. Then Zillow got sued because it was undervaluing some homes. For example, my home is surrounded by homes which are all about 1.5, 1.6, $2 million homes. But guess what Zillow put as the value of my home? It put a value of approximately about 300,000. Now, how can you have a yeah.
That's bad.
And ironically, the reason it put that value is because my home is so big. In other words, the backyard is close to 28,000 square feet. Now, in big cities, in Fremont, you don't usually find homes with such a big backyard. Right? So Zillow looked for something called a comparable home. And I'm just guessing that the comparable home was far away in some rural area where somebody's home had such a big land attached to it, 28,000 square feet attached to it. And so it was looking at the value of that, maybe God knows, Fresno or wherever it was, right? That home and attaching that value to my home. So, so all these algorithms have imperfections to them. None of them quite work well. And so you're forever improving it. And Zillow, after the lawsuit and so forth, I suddenly noticed that they have gone and corrected, in quotes, corrected the value of my home, though any real estate agent would tell you that it's still severely underrepresented. So it goes on like that, it goes on like that. You're never done with the problem. If you think of Zillow, a large team of data scientists are trying to solve only one problem on only one data set for their entire career. So you see that, Patrick, how it works in real life.
Yes, sir. That's what I was trying to understand because there are so many data sets every time we go to take lessons for machine learning. So many data sets after data sets. That's what I wanted to know. Like in the real world, how many data sets is really what do you touch? What do you work with? And yeah, like you said, it's not as many as you think because fine tuning is much better.
Exactly. In fact, usually for one startup, one data site is their entire livelihood, and it's their ticket to a successful exit, multi-million-dollar exit. Also, the game is very interesting these days. As you know, recently the trend has been in Silicon Valley that you don't acquire a startup for the business, the money. Right? The moment you see proven talent in any startup, you just acquire them. And you couldn't care less with their business model. You just want proven talent. So a lot of the time, what happens is a lot of bright people get together, do a startup, They start solving a problem. They prove that they have done a pretty good job on one problem, and the problem may have absolutely poorly defined business model attached to it. Sometimes people have no clue how they're going to make money out of that. And yet, there is a very successful exit because the likes of Google couldn't care less what this little company is doing, but they do care a lot about picking up talent. Everybody knows, in fact, I am in this space, I research this topic. Everybody knows that when you interview people and look at job applicants and resumes, you hire mediocre people. The only way to hire talent is through acqui-hire. I mean, the probability that you'll hire high quality talent through interviews and resumes, very small proportion. You do end up hiring some very good people, but a much smaller proportion than when you just go acquire talent through acquisition. Right? So acqui-hire is the new way of hiring these days. And so I would highly encourage you, become good with any few algorithms. Take a data problem, sit on it for months, become good at it, publish a couple of articles, right? Do a startup on it, and then sit back, relax, and wait for these companies to come to you. I'm saying it from the experience of my friends.
Yeah. Getting back to ML100, could you in one place list all the labs that should have been work that should have been completed for the class in case some students overlooked which assignments, because sometimes it feels a little fuzzy?
Yeah, sure. Definitely, guys, the tabular data.pdf, every single example that is there, you should do. That is the core textbook for you for the labs.
Okay, that's
So you have clustering. That is it. That is your lab book. Do everything that is in the lab book. If you have done everything there, you haven't missed much.
great.
By the way, how did you find the lab notes, guys? Did you find it useful? Any general feedback from the newer students? Patrick?
Yes, sir. I was able to understand the lines of code, and I was able to try to answer most of the labs. I haven't finished everything yet, but yeah, I'm doing it at the same time reading the book. So.
Nice. How about you, Balaji? How did you like the book? Balaji, are you here? I think he may have stepped out. How about you, Suresh? How did you like the labs and the workshop in general?
The classes were very good. I've not fully completed my lab, but the labs are good. The only thing I think, after every class, if I can find one or two areas where to apply that topic that I learned in the class, that always gives a good understanding. Sometimes I'm just still struggling with just doing what is in the lab, and I mean, whatever is in the lab is good, but my motivation is not up to the mark to try all the labs. So I need to work on that. And probably one other exercise that I did is, if you find one or two problems related to the theory that I learned, that helps me to just spend more time than at the lab. So I need to combine those two. But overall, I think it was a very good learning experience, and I was exposed to a lot of things that I do now. So
Nice. Thank you, Suresh. How about you, Shiva? How did you like it?
So I really like the whole concept of the lectures and the labs. So you're particularly asking the labs, right? So is it correct, Asif, or you're overall
And in
asking
general,
for that?
yeah.
Yeah, in general, I mean, it's very, very, very informative. I would say, like, I mean, I wouldn't have gathered that much of information anywhere, reading a book or attending another lecture or anywhere. So I'm really indebted for the information that you have spread, I mean, provided us. So the labs are really exhaustive. I think I still have to catch up with the labs. But overall, it's a very good experience. I would like to continue with the other workshops that you're planning in future too. So
Thank you. All right, guys. Anybody has any other comment? Otherwise, we'll. Oh, Aditya, you are the. I don't think it's Manisha, isn't it?
I'm sorry.
No. Oh, she's
Yeah. How did you like the workshop?
Yeah, I mean it was pretty advanced. But yeah, I didn't enjoy it. I did enjoy it, yeah.
Nice, very good. All right, guys. So I'll post this video, and I'll post this PDF also, the last article. And do stay in touch. Remember, guys, the workshop is over, but I hope our relationship is not. You can reach out to me anytime you want, months later if you wish, with your doubts, with your questions, with clarification. I'm always there. Huh?
Any
And do
additional
please.
books that you would recommend for M200?
Yeah, it's the
Any
same text.
additional books that the same
No,
textbooks? Okay.
what we'll do is we'll finish it, and the lab books that I recommended, we'll do a lot from those labs also. Now, what happens is that ML200 will cover the topics that are there in this textbook, but it will also cover things like no free lunch, etc., for which actually, unfortunately, there are no good textbooks, which is the limitation. So I'll be giving you a lot of notes that I have written. Let's see if they are of some use, and take it from there. See, now as we go to 200, 300, and so forth, we'll be getting into very recent territory, and usually things which are hot and new, you don't get textbooks on them easily. They're too new. And the ones that are there are too mathematical. They'll explain it, but they'll explain in such high-flown language that without the mathematical background, you're completely confused what exactly was said. So it needs
Yeah,
to be
last
brought
year.
down.
Yeah.
Needs to be brought down that people understand. So we'll try that. And guys, all of these videos you have access to. A couple of them I haven't shared yet because YouTube there was having a problem recently. I tried to share a couple of times. Each time I would do, for some weird reason, it would not let me enter the list of people I could share it with. Let me try it again. Oh yeah, I succeeded this time. Excellent. So I'm going to share the rest of the videos with you guys.
Yeah, as if the last 3 videos are still not viewable.
No, yesterday also when you pinged me, Anil, I tried to share. I couldn't once again do it, but now, just now I tried again, and I noticed you can share now. So I'm adding it right now. Huh?
Okay.
So you guys should get a notification in a few minutes. It has all been shared with you. I apologize. This. So in fact, one notification you should get literally right now. See if you guys got a notification.
Notification by email or Slack?
Usually it comes by email.